This is going to be a content-heavy section. We're going to state the important rules of exponents, and then we'll look at many examples that illustrate how to use these to do some algebraic simplifications. Okay, so let's look at these rules. We have a to the x plus y equals a to the x times a to the y. So here the base is the same for everything. It's all base a. But the exponent varies. I have x plus y on the left, x and y separately on the right. So this is the rule for same bases, different exponents. Well, I can look at sort of the reverse scenario in which I have different bases but the same exponent. And we can play a similar game. A to the x times b to the x is the same as if you multiply a and b together and then raise it to the x power. Okay, so this is different base, same exponent. A very interesting one, I think, is what happens when I have an iterated exponentiation. When I have a to the x to the y. What do I do with these iterated exponents? Well, I multiply them. Okay, so I think this one is worth looking at some examples. What is 2 to the 2 to the 2? So I've iterated this. Right, so this is the same as saying 2 times, or rather 2 to the power, 2 times 2. So 2 to the 4, which, if you remember your powers of 2, your dyadic numbers, which are good, especially for the computer scientists among you to remember, this is just 16. Okay, so what we did here is said that this goes to 2 times 2, and we see this down here. Okay, so it's important to remember how these iterated exponents work. Now, the last rule is something that in mathematics we might call a convention. Okay, there are reasons for setting this rule to be what it is, but it's maybe not obvious the first time you see it, which is what is anything to the 0th power? Okay, anything to the 0th power we set to be 1. Right, so we sort of have already seen this with degree 1 polynomials, or rather degree 0 polynomials, but I thought it was worth iterating again in this context. Okay, some things are worth stating twice, and I think this is one of them. Okay, so now what I would like to do is look at a variety of examples that illustrate how these rules can be applied. So let's start with something relatively simple. 2 to the minus 3 times 2 to the 3. So this is the same base, different exponents. So what do? I say that this is equal to 2 to the minus 3 plus 3. Same base, so I add the exponents. What is minus 3 plus 3? 0. So I just get 2 to the 0, and then by my convention, this is 1. Okay? So in this case, all I had to do was remember that to multiply exponentials with the same base, I just add the exponents. So here's a slightly more complicated one. I have 2 to the 4th times 2 to the minus 1 to the 3rd. So I'll use my order of operations, and I'll deal with the parentheses first. So I'll say this is equal to 2 to the 4th times, well, what is 2 to the minus 1 to the 3? How do I deal with iterated exponents? Well, I multiply them. So this is 2 to the minus 1 times 3. I'll simplify that to 2 to the 4 times 2 to the minus 3. Okay, so some of the work is done, but now I'm back in a similar situation to my previous exercise. I have the same base, different exponents. How do I resolve this? Well, I add the exponents. Four plus minus 3 is 1. So I get 2 to the 1, which is, of course, 2. Okay. So in this case, I just had to carefully apply the order of operations, one of the first things we studied, along with the rules for exponentiation. And I was able to simplify this efficiently. So here's a cute example. It's going to combine some of the stuff we saw in the very first submodule on roots. So I had the square root of 3 and the square root of 27. Now, individually, both of these numbers are a mess. we'll see later in the course that they're both irrational numbers. They're very long decimals that never repeat. So it doesn't seem like there's an obvious simplification here. But something one can notice is that, just recalling that the square root of x is equivalent to x to the 1/2, this is really a problem about exponents. So I have 3 to the 1/2 times 27 to the 1/2. So why observe this? Well, now I'm in a situation I know how to address. I have the same exponent, different bases. How do I combine these? Well, I multiply the bases. So this is 3 times 27 to the 1/2. 3 times 27, maybe you know this, maybe you don't. Maybe you write out the multiplication by hand. Right, this turns out to be 81 to the 1/2. Maybe it's more recognizable if I say, what's the square root of 81? What number squared gives me 81? 9, right? So this turns out to just be 9. Okay, so I have sort of two very ugly numbers at the beginning, square root of 3 and square root of 27. But when I multiply them and use my algebraic tricks, actually they're more than tricks, they're basic principles. When I use the basic principles, I just get a nice clean number like 9. So here's one that's pretty abstract looking, but this is sort of, I think, very representative of what you might see on the clip. Okay, so I have a to the 4th times b squared times a to the minus 1/2 times b to the minus 3. So for this, I'll group it as a to the 4th times a to the minus 1/2 times b squared times b to the minus 3. So why did I sort of rearrange it in this way? Now I can easily use my rules of exponentiation and say that, okay, same base, different exponents. So I have a to the 4 minus 1/2 times b to the 2 minus 3. So 4 minus 1/2 is also known as 7/2. And this is b to the minus 1. And there's nothing else to do. Okay, so again, very abstract looking, but with a quick rearrangement and application of my exponential rules, simplifies quite cleanly. All right, so here's another sort of more abstract looking one, and we'll try to play the same game. In this case, just notice that all of these have base x. So I have 3 exponentials, all with the same base. Just add the exponents. Now I'm adding 3 things together. Right, so this is equal to x, and what's the new exponent? It's 1 minus y plus 7 plus minus 6. So I put everything together, and let's see here. I get 1, the y's cancel, and I get 1 plus 7 minus 6, so just x squared. Okay, again, at the beginning of the problem, there was a variable in the exponent. Things were weird, but I just applied my rules, my basic principles, cleaned up beautifully to just a simple polynomial. Okay. Something similar. Now I just have different bases, all of which are constant, and I have different exponents as well. So how could I do this? Well, it doesn't look so obvious, right? But I can say, well, let's first address these. Okay, so this is same exponent, different bases. What do? I multiply the bases. So 3 times 2 to the x, and then I'm still having to deal with 6 to the minus x. I'm not going to touch it yet. It doesn't really fit in with any of the other ones. What is 3 times 2? 6. And then magically almost, or I wrote the problem so I knew it would work out this way. Something that was intractable at the beginning now becomes very clear. I have a same base, different exponents here, so I add the exponents. And I'm stuck with 6 to the 0, which is of course 1. Again, so I'm in a situation where At the beginning, it looks quite complicated, but by applying these rules, it simplifies nicely. Just as a remark, it would have been tricky to try to do 2 to the x times 6 to the minus x. We don't really have an obvious rule for that, because both the exponents are different, x and minus x, and the bases are different, 2 and 6. So we really needed to sort of proceed in the order that we did. We needed to first address 3 to the x times 2 to the x, and then we could deal with 6 to the minus x. Okay, just one more exercise that's kind of the killer one here. We have a whole lot of stuff going on. Let's try and play with these rules. Okay, so I have x to the 2 times x to the minus 3 divided by x to the 5. And then also x times x to the 4th divided by x, and then times x. So let's clean this up. Okay, so I have x squared times x to the minus 3. Same base, different exponents. Add them. Okay. How do I deal with this? Well, I'll deal with it at the end. So now I have x to the minus 1 over x to the 5th. Notice that the x cancels here, so I have times x to the 4th. Okay, and then this is equal to x to the minus 1 times x to the 4 over x to the 5. I add the exponents here, and then get x to the minus 2. Okay, so again, in this case, it was just a matter of keeping track of all the different exponents and knowing how to cancel everything out. So of course, this is a nice place to remark that dividing by x is, of course, the same as doing x to the minus 1. Okay, so this is a nice trick if you have sort of negative exponents involved. Okay, it's just the same as dividing by something.